All right, logistic growth part 2. So in the last one, we talked about our differential equation for logistic growth and our function y is a function of t for logistic growth. So let's look at some more examples of how we're going to need to be able to use these. Right? It says on the AP exam, maybe given questions that require you to recognize the parameters of logistic growth for either equation or the differential equation written in a different format. This requires you to manipulate the equation to fit one of the two standard forms. Think about like going back to like quadratics, where you've got standard form, you've got vertex form, you've got factored form. Think about there's different forms of this equation. We're going to want it to be in one of the two that we've already looked at, okay? The differential or the function y is a function of t. So let's look at a couple of these. Example 2, the growth rate of population P of bears in a newly established wildlife preserve is modeled by the differential equation. dPdt equals blah, 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 where t is measured in years. All right, it's really important that you guys know these two forms here. Don't assume you're going to be given either of these forms, okay? So study these, make sure you know these. Because when we're given a function like this, that's a differential equation, then we need to be able to see that that's not in exactly the same form as this. Okay, in our differential equation form, we need our y variable, which in this example is p, population. We need that to be by itself as this second term inside those parentheses. So we're going to have to manipulate this in order to get it in this form in order to see exactly what our L and K values are. Because right now, 1 and 0.8 are not our L and K. Even though they're in the right position, we've got to get it in this form first. So the way that we do that is a little bit of finessing. So we're going to say, all right, I want that P by itself is the second term inside the parentheses. It's being divided by 100. So to get rid of that denominator, I need to multiply it by 100. So we multiply both of those terms inside the parentheses by 100. We can't get away with just doing the P. But we've just multiplied that whole piece by 100. So to keep it balanced, to keep it so that we're not changing the value of that function, we also need to divide the function by 100. The way we're going to do that is just divide the term outside of the parentheses by 100, right? Not the inside. So we're multiplying the inside of the parentheses by the denominator of P, dividing the outside by that denominator, so that we're essentially just multiplying by a form of 1. Okay, so what that gives us is it gives us this form. It gives us 8 thousandths P times 100 minus P. Okay, we've got our P or our Y by itself. We've got a factor of it on the inside and the outside of our dy dx, or dp dt in this case. So now we can accurately pick out, this is our L, our carrying capacity, 100, and this is our K value. All right, so now we can actually answer the questions based on our form of our differential equation. All right, so what is carrying capacity for bears in this wildlife preserve? Carrying capacity is our L value, so we just go to our equation and we hunt it down, boom, 100 bears. B, what is the bear population when dPdt has a maximum value? That's our rate. Maximum value is when it's at the halfway up the carrying capacity, right? At that inflection point where it goes from increasing at an increasing rate to increasing at a decreasing rate. All right, so just take that L, cut it in half, 50 bears. C, what is the rate of change of population when it is growing the fastest? Rate of change, that's our differential. All right, if we had our y equals equation, we could do our inderive like we did in the last example. We've got our derivative, our differential now, so we can just plug in that population for P and find what that is. 20 bears per year. Make sure you plug it in both places. Simplify, make sure you do order of operations. 20 bears per year. All right, that's at that inflection point. All right, example 3. Suppose that a population develops according to the logistic differential equation. All right, they give that to us, dp dt, where t is measured in weeks and t is positive. Okay, 0 or positive. So again, they don't give it to us in the form that we want. So the first thing we need to do is get it into that form. All right, so this is what we're aiming for. We've got just two, we've got a binomial essentially here. We need a p or y, however you want to look at it, outside and inside. So factor out that common p. That p on the inside is being multiplied by some value. We need it by itself. So let's divide on the inside by that value and then multiply on the outside by that value. All right, we're kind of doing the inverse of what we did in the last one because we've got a multiplier here instead of something being divided by. Okay, if you rewrote that as 1 over or 2 over 1,000, then you would just have to multiply by the reciprocal. All right, so now we've got it in this form here where we can pick out our L as 100. We can pick out our K value as 2,000s. Okay, so now we can address the questions they're asking us. Hey, if P naught equals 5, what is the limit as T approaches infinity of the population? All right, so again, as the population is going out, time is moving. What's going to happen? Well, it's going to approach that carrying capacity. All right, it's going to approach our L value, which we see down here is 100. Okay, it doesn't actually matter what the initial population is. It's always going to approach that carrying capacity as time goes on and on into the future. Okay, which is what all three of these are doing. The limit of a logistic as time increases without bound is going to be that carrying capacity. All right, but something interesting is happening here. In part D, they say sketch the solution curves for A, B, and C. Which one has an inflection point and why? So let's see what's happening here when we look at our slope field for this differential. Okay, so here is a slope field generator that I pulled online, and I put in our given differential equation here. And here's what we're looking at. All right, I've got my window from 0-ish to 50, 0 to 150 in the vertical direction. So notice that we've got our carrying capacity here at 100, and we've got, again, that kind of, the slopes are pushing in both below and above, which we never see with the logistic, towards that carrying capacity. So let's see what happens. If I plug in an initial value 0.5, which is what part A asks us to do, there's what our function is going to look like. All right, that's what we expect for a logistic. If I do the next one, which is 0.60, all right, there's what it's going to look like. Again, think about, we've got our general solution. We're looking at particular solutions now as we add that specific point. Okay, that one also approaches 100. And then the last one is when our initial population is 120. All right, that's above. It starts out above the horizontal asymptote. But again, think about the context behind this is we have the same relationship that that this population does over time, and we're applying it to different initial populations of whatever, cities or whatever, or forests if we're talking about animals, whatever. And in these two, we've got that initial increase in population because the environment can handle more of this thing. Up here with this 120 initially, the environment cannot handle that much of that population, whatever that thing is, people or rabbits or bears or whatever. All right, so it immediately starts to decrease, but it can handle 100, so it levels out at 100. All right, I thought that was cool looking at those. So the question asks, which one of these is going to have an inflection point? A, because it is the only one that starts below that halfway line, right? Halfway is going to be at 50. This initial population at 60 doesn't start below 50. All right, so this is the one that's going to have it, and it's going to be somewhere around here, whatever, 15-ish years. All right, last problem real quick, example 4. They give us a rate at which a flue spreads. This time they give us dp dt. It's in the form that we want. We need to solve for p as a function of t. So go ahead and pull out your L, pull out your K values. We don't have C, so you're going to have to solve for it, plug it in just like a particular solution, solve for it, and use that to answer B and C.